Picture a reservoir of water so massive it contains 140 trillion times the volume of every ocean on Earth combined. Astronomers located this colossal vapor cloud deep in intergalactic space, exactly 13.6 billion years in the past. According to the standard cosmic timeline, the first stars formed when primordial hydrogen gas slowly cooled and collapsed under its own gravity. But at 13.6 billion years ago, the universe was too hot and dense for hydrogen to clump together. The background temperature stayed high enough to keep the gas in a state that prevented star formation. This creates a problem for the elements. Without the pressure of a star's core to fuse lighter atoms together, there is no way to create heavy elements. Oxygen, the essential ingredient for water, should not exist yet. This creates a direct contradiction. We are seeing an intergalactic ocean, millions of light years wide, in a time frame where the standard model suggests its primary ingredients had not yet been manufactured. The presence of this 140 trillion ocean cloud suggests that our current simulations of the early universe are missing a critical mechanism for star formation. This paradox has led to a new framework from Nathaniel Faxon-Cherrier, the Cosmic Helium Evolution Theory, or CHET. CHET proposes that the earliest stars weren't fueled by hydrogen at all. Instead, it was dense pockets of primordial helium-4 that triggered the first wave of fusion. Helium-4 responds differently to high temperatures, allowing it to collapse even when the environment is too hot for hydrogen. Cherrier's models show these helium-rich regions forming massive stars, 262 times the weight of our Sun. Because of their extreme density, these stars burn through their fuel in millions of years rather than billions. They lived at a pace that allowed them to finish their entire life cycle while the rest of the universe was still cooling. Inside these cores, fusion worked rapidly to smash atoms into heavier and heavier elements, eventually forming a dense iron center. By utilizing helium-4, the early cosmos bypassed the temperature constraints of hydrogen, forging complex elements in a fraction of the time predicted by previous models. Using the flash physics simulation, researchers modeled a 262 solar mass helium star to see what it would leave behind after its death. The simulation shows the star's life ending in a supernova, releasing 10 to the 53rd ergs of energy into the surrounding space. As the shock wave expands, the simulation measures the chemical output. This explosion expels 5.2 times 10 to the 44th kilograms of newly forged oxygen into the void. This expelled oxygen collided with the sea of primordial hydrogen, filling the early universe, mixing at extreme temperatures. Calculations show this exact collision produces a massive water cloud weighing 5 times 10 to the 44th kilograms, perfectly matching observations. This simulation provides the chemical mechanism required to produce the massive intergalactic water cloud we see in the ancient universe. The implications of the theory reach further than a single water cloud. Helium-4 appears to be the primary engine that shaped the early structure of the universe. Density fluctuations in this primordial helium determined how galaxies would look billions of years later. Modern elliptical galaxies contain 2 to 3 times more helium-4 than spiral galaxies. This abundance of helium also explains the rapid growth of the first supermassive black holes, providing a dense source of material for them to pull in early on. We previously viewed the early universe as a dark, dormant space, waiting for the right conditions to change. The data now suggests it was a highly active environment. 13.6 billion years ago, the universe was already forging heavy metals and filling the void with cosmic oceans through the power of helium fusion. To see more of how the early cosmos was built, make sure to like and subscribe to MDU.